Today we're going to talk about how to solve second-order differential equations using the Laplace transform. So these are examples of the types of equations I have in mind. D squared y over dt squared plus p dy dt, where p is a constant, plus qy is equal to some driving term, say f of t. So these are our damped oscillators. P is the damping constant. If P is 0, it's an undamped oscillator. And Q is, of course, the spring constant. Okay, so in order to use Laplace transforms to do this, we're going to have to find out what the Laplace transform of the second derivative is, right? We know the Laplace transform of the first derivative, so let's see if we can figure out what the Laplace transform of the second derivative is. Now, this may seem hopeless, except if we remember, a second derivative is just a derivative of a first derivative. So using the Laplace transform property for derivatives, we get s times the Laplace transform of the first derivative, dy over dt, minus the derivative's value at 0, and then we just iterate and do this again using the Laplace transform rule for derivatives. We get that. So we have s times the quantity, the Laplace transform of dy over dt, minus y times 0, and then subtract from that y prime. And let's gather our like terms so we know what we've got here. We've got a total of s squared Laplace transforms. Oops, this should be a y. S squared Laplace transforms of y minus s times y's value at 0 minus y prime's value at 0. And you'll see these are the initial conditions that we have for second order equations, y at 0 and y prime at 0 usually. Okay, so that's a start to figure out what's going to go on here. So now we should trust that we should be able to use the same sort of process we were using before to solve first order equations, to solve second order equations. The main difference here is the types of driving terms we're going to use. Before we were often using exponential driving terms or constant driving terms. Of course, for second order equations, often we want to consider periodic driving terms. So in order to do something like this, we're going to have to know what this Laplace transform of the sine of omega times t is. All right? This is a sine function with period 2 pi over omega. And we'd like to know what the Laplace transform is. Right? Well, we could use the formula that defines the Laplace transform, that integral transform. That's going to take some work. It's doable though, but it's actually a lot easier to remember that the second derivative of sine of omega t is equal to negative omega squared sine of omega t. Okay. So we're going to use that here. So let me clear this out. Using that property and taking the Laplace transform of both sides, we would get the Laplace transform of the second derivative of sine of omega t is equal to negative omega squared times the Laplace transform of sine of omega t. This is because omega squared, negative omega squared sine omega t is the same thing as the second derivative of sine omega t. And remember, omega is a constant, so it comes out of the Laplace transform. It's not a variable in this situation. Okay, now this on the left-hand side is the Laplace transform of the second derivative, and we just calculated what that is. That should give us s squared times the Laplace transform of sine of omega t minus s times the value of sine omega t at 0, which is 0, minus the value of the derivative of sine omega t at 0. The derivative of sine omega t is omega cosine omega t. Plugging in 0, we get cosine of 0, which is 1, so that omega stands. And that is going to be equal to negative omega squared Laplace transform of sine of omega t. Now, you'll notice the only mystery is the Laplace transform of sine omega t. So if we just solve for the Laplace transform of sine omega t, we'll see what we got. It is going to be omega over s squared plus omega squared. All right, so there is our Laplace transform of sine of omega t. That's great. And a similar calculation will give the Laplace transform of cosine of omega t. And that is s over s squared plus omega squared. There, and we get this s. Here we get the omega because it's the first derivative of sine, which is non-zero. Here we get an s because the value of cosine at 0 is 0. So that's the difference between the two. Okay, so that's great. We've got the Laplace transforms of our two most common driving terms that we've been using for second-order equations. So one more thing that turns out to be useful for this is another property, and let me talk about that. This is related to a time shift. So we've got the Laplace transform of sine and cosine. Another thing that's going to help is if the Laplace transform of some function is, let's call it capital F of s, right? We take the Laplace transform of f, we get capital F of s. Then, if we were to take the Laplace transform of the exponential function e to the at times f, now we want to know what we get, because sometimes we've been driving with exponentials times sine or cosine. Here, this is related to the time shift we looked at before when we were dealing with discontinuous functions. This is just a time shift of f by a. Okay. So this will come in handy. For example, now we could calculate something like the Laplace transform of e to the minus 3t cosine 2t. This is just going to, well, what's the Laplace transform of cosine 2t is s squared, or s over s squared plus 4, right? That's what we get when we just take the Laplace transform of cosine 2t. But now, because of this e to the minus 3t in front, we're going to evaluate this at s plus 3. Okay. A is negative 3 here, so we evaluate it at s plus 3. And what we get out of that is s plus 3 over s squared plus 6s plus 13 when we square the quantity s plus 3 in the denominator. Okay. So these are all the basic tools we are going to need to solve these sorts of problems. So let's take a look at a simple second order problem and see if we can solve it here. Our second order problem is going to be the second derivative of y with respect to time plus 4y is equal to 3 cosine t. So here we have an example where we have no damping. Right? This is an undamped oscillator, and let's set y at time 0 to be equal to y prime at time 0 to be 0. So we're starting from rest. We're going to drive by this 3 cosine t. All right. So we take the Laplace transform of both sides. The Laplace transform of the second derivative is s squared times the Laplace transform of the first derivative minus s times the value of y at 0 minus y prime at 0. This is all just this Laplace transform of the first derivative. Then we get 4 Laplace transforms of y. And that is equal to 3 times the Laplace transform of cosine. The Laplace transform of cosine is s over s squared plus 1. Okay? So note that y at times 0 is 0 and y prime at times 0 is 0 here, so those terms vanish. And we get the Laplace transform of y. On the left-hand side, we have s squared plus 4 of them, so I'm just going to move those to the other side. So this is going to be 3s over s squared plus 1 times s squared plus 4. All right? So there is our answer for the Laplace transform of y. Now, of course, we have to solve for the partial fraction decomposition. This one's actually not that bad. Okay, if we have opposite signs here, we'd cancel out the s squared. And then what remains, we have 4 and 1. But 4 minus 1 is 3, right? So this says, okay, this is not so bad. There we go. You can check that there, but there we have a nice answer. And this is not so bad now. Now we know what y is. Right? These are directly related to the cosine transform. So the first one, negative s over s squared plus 1, is the transform of negative cosine of t. The second one is the transform of cosine 2t. Using the formula. So there's our solution. We solved that second order equation using Laplace transforms.